Hello, everyone. So now let us begin with the first plenary session of CEPOC 2021. And the activities today will be all in English, as we have some special guests from outside of Brazil. And the first activity that we are going to have at CEPOC 2021 today is a plenary session that is going to be held by Dr. Celanovic from Typhoon. So we will begin these activities with this very interesting plenary session. And then we will move on to a panel discussion in which we will have more guests invited to participate, to present their works, and we will have some time for questions and answers. So beginning by the plenary session, we will begin by, first of all, thank all the attendees for coming to see this first activity. And also thanking Dr. Celanovic from Typhoon that has accepted our invitation to present his talk today at CEPOC. So thank you very much for all of you that are attending this plenary session, and thank you very much, Dr. Ivan, for accepting our invitation. So I will begin by reading Dr. Ivan's biography. Dr. Celanovic is the co-founder and Chief Business Development Officer, CBDO of Typhoon, and was a member of the team that developed both the theoretical foundation as well as experimental validation of the world's first 1 microsecond ultra-low latency hardware-in-the-loop real-time emulator for power electronics and microgrids. He is responsible for technology and product development vectors as well as business development. Dr. Celanovic also co-founded Mesodyne, that is commercializing solid-state portable power generators. Dr. Celanovic has published over 80 journal publications, 5 patents, and 2 book chapters. He holds a Doctor of Science degree from the Massachusetts Institute of Technology in Cambridge, and a Master in Science degree from Virginia Polytechnic Institute, and a Diploma Engineer degree from the University of Novi Sad, Republic of Serbia, all in electrical engineering and computer science. So this is the introduction for our first panelist. And now, Dr. Ivan, please feel free to share with us your presentation.
Thank you, Fernanda. Thank you so much for such a kind introduction, and thank you so much for inviting me. It's first and foremost, I have to commend you for organizing this event, and really keeping the audience and keeping the community engaged and excited about the future. And also thanks for giving me the opportunity to share some of my thoughts today, kind of what we have been seeing, where the grid is moving, and what our thinking is. And I think I'll probably keep it more open-ended. Hi, Fernando. Sorry, I think I had a crash here. Can you hear me now? Okay.
We can hear you and we can see you. You just need to share your screen again.
Okay. So 1 second. Okay. Good. Can you see my screen?
Yes. Yes.
Okay, great. Yeah. Hopefully. Hopefully it's not going to happen again. I'll stop the video just to make sure things are I guess getting smooth, and then please jump in if if something is not showing correctly. So what I would like to talk about today is really thinking about where the grid is going, where the future is, and what are the kind of revolutionary changes that we are seeing now after probably more than 100 years that we've been experiencing, working with, and enjoying the benefits of the grid. So we'll talk a little bit about the history, kind of like challenges going forward, and opportunities, really, kind of like what can we do as engineers, as developers, as a community to accelerate this transition and to make it more interesting. I kind of broken down the talk into kind of four sections. First, I'll talk a little bit about US grid evolution, kind of like from early, even before 1920s to today, kind of spanning this period of 1 century. And from there, we'll move on to what I like to call D3, decarbonization, digitalization, and decentralization of the grid, because these are these 3 trends that are really driving the majority of the changes and driving the new prospects. After that, we'll talk a little bit about microgrids, and I really see microgrids as a sandbox for future grid, because all these new technologies, all the new changes that we are seeing, be it digital control, be it advanced inverters, be it distributed control and communication, all of these are being applied and kind of like tested and validated inside this sandbox before people are trying to scale it further to the larger grid. And we'll also talk a little bit about the advanced control of inverter-based DERs, kind of like as a as kind of like a natural building block there. So just a brief history without I don't really want to overwhelm you with this, but just for me it's also kind of always interesting to look back and to think, what's the road that we have traversed, what's the road that we have traveled in this past probably now it's almost like century and a half. So really the first kind of concept, or the first thing that could be called grid, was 1882, built by Thomas Edison, and it was a DC system, as all of you guys probably know. It was installed in New York City and served about 59 customers. Believe it or not, it was in the Wall Street area, so somehow it made its way to to the right place. Yeah, and the interesting thing is that this was kind of like one of these first clumsy DC systems where they're relatively low voltage. There were a lot of problems, but the concept of being able to generate and distribute electricity within some area or some smaller area was kind of like first experienced. And then, of course, one of the major changes and major shifts was 1896 with Westinghouse and Tesla, when they really started Niagara Falls hydroelectric power plant development. Of course, this was fueled with development and the development and demonstration of transformers, which was kind of like the critical piece. And that first transmission from Niagara Falls was actually to Buffalo, and it was really kind of it was really revolutionary change, because you could step up the voltage and you can distribute electricity on to longer distances. After that, they draw the first transmission line all the way down to New York City, and the rest was history. With kind of electrification, always we were seeing kind of this constant push to increase the voltage. So I kind of find this really interesting milestone. In 1922, in US, the first 245 kV line was commissioned. So maybe less than 30 years after the first hydroelectric power plant was built, we're already seeing 245 kV line commissioned. Now, the thing which is kind of interesting to think about here is like how did the utility grid develop after that? And most of these transmission lines and generations and distribution kind of companies, most of them were basically vertically integrated, and they were regional. But one kind of important movement was in 1935, the Federal Power Act empowered basically the Federal Power Commission to regulate the wholesale transmission and sale of electric power, and that's really something that started to change the landscape and really start to fuel the drive for taking advantage of efficiencies of scale. 1927, another really important milestone is 3 major utilities established the P&J interconnection, and this is what we know today as PJM. So basically, Pennsylvania, New Jersey, and Maryland basically formed this regional transmission organization. So now we are seeing kind of, okay, well, we were start building this big hydroelectric power plant. We were building these transmission lines to serve our customers. But now we are seeing that, okay, well, networking effect. Okay, can we get multiple generators together? Can we get multiple transmission lines together? Can we do things smarter? So kind of like from point to point, where the network, there are not just the technical conditions that needed to be satisfied, but also, government, they had to regulate, and that had to kind of like enable this. And these were kind of like the building blocks after which the network started really expanding and connecting. And I will just introduce one more kind of like, in my mind, huge milestone. This is kind of like late 90s, at least in US. The theory of spot pricing was basically introduced, and that provided the foundation for successful market design. So basically, there is this framework that was really developed initially by Fred Schweppe and his collaborators. He was professor at MIT. And this is a framework known as bid-based security constrained economic dispatch. And it was really revolutionary because it really enabled the central coordination by the system operator, and combined with decentralized decisions by market participants. So you kind of have this central coordination that enables the system is working, but kind of like free entities can participate really freely and decide how they want to engage in the process of selling and buying electricity. So this was kind of towards this process of the deregulation. So one of the parameters that we like to look at, if we're kind of trying to measure and kind of gauge this grid, is okay, well, did we do a good job? I mean, was this a good thing that we started, from these kind of point-to-point networks, and then over time we start developing this really complex mesh, interconnected mesh of generators, transmission networks, and users, distribution subsystems. And one parameter that we can look at is really the cost of electricity. Now, of course, this is normalized, and we can see kind of like from early 1920s to today's day, kind of like a steady decline in the prices, and then kind of like leveling off at some kind of standard plateau. Yeah. The other thing which we started noticing very early on with this networking effect, when people started to interconnect a lot of synchronous generators, that there were problems, and the problems were how do you parallel them, how do you control them, stability issues, and so on. And one interesting character was this guy, Professor Vannevar Bush, who was professor at MIT in the early 1920s. And what he did is basically he developed the first analog computer called differential analyzer. I mean, remember, there were no transistors, there were no digital computers at the time. And one of the first applications for this differential analyzer was really trying to help a couple of researchers at General Electric to try to simulate some instabilities that they were seeing on their power network. And kind of an interesting note, you start building this very complex network system, complex for the time, and you start seeing some emergent behaviors. And what do you need to do? I mean, you need to go back and build some tools that will help you analyze and test and figure out how do you improve this, how do you stabilize, can this grow or not? And it's really one of the a lot of literature really calls this the beginning of scientific computing. And power grid, interestingly enough, was this first toy problem, or maybe not so toy. Interestingly enough, one of the collaborators of Professor Vannevar Bush was Edith Clark, that at the time worked in GE. And probably a lot of you know that Clark transformation was actually invented by her, and it was really a groundbreaking transformation. Later on, you had like symmetrical sequences and so on that actually enabled us to analyze and get more insight into the operation of the system. She was using differential analyzer to kind of understand a little bit better what this Clark transformation is bringing to the table. So I kind of thought that this was, this is a really nice kind of historical side note that kind of connects the academia, the problems of the time, this large growing power network, and certain outcomes. So basically, how does the electric power system look like now? What did we end up with in this process of starting kind of from Edison's DC grid and then moving to Westinghouse Tesla's AC transmission? So basically we started centralizing power generation at these really large big generating units, and then distributing the power through the transmission network, and then having the kind of the distribution networks kind of purely passive or mostly passive, where they were just kind of loads trying to kind of connect, regulate a little bit the voltage, but all the generation was really at the top with large massive generating units interconnected with the transmission lines, I would say very centralized, and then kind of like relatively simple and dumb network of kind of quote unquote passive loads. We should not underestimate the effort. National Academy of Engineering names the utility grid as one of the most complex and most impactful man-made systems on the planet, and certainly there are good reasons for that. But one kind of question that always comes to my mind is like, okay, well, the grid that we ended up with is highly networked grid with highly centralized power generation. Is it good? I mean, did we converge to the right solution? Is this good for us? Is this good for customers, for consumers? And there are different parameters how we can look at this. But one, for example, typical parameter is like looking at transmission and distribution losses, kind of as percent of the total generation. So this graph to the left, if we're taking a look at it, so we basically see a steady decline of losses as the portion of total power generated on the grid, and you can kind of see almost a linear steady decline from 1920s all the way to today. The other parameter how we can kind of like look at this is how are these different networks in different countries in different geographical regions, how are they're faring and comparing, and that kind of being plotted as basically as a function of population density. And you can see here pretty kind of well, I would say kind of like well centered result. Most of the grids are operating at very similar overall efficiencies. Here and there you can see some outliers, but basically depending kind of like on the spread of population, we're talking about kind of like 7 to something on the order of like 4% losses. But you can see that for example in South Korea, the density, population density is much higher. Yeah. Okay. The other parameter is that we want to look at. Okay, so we built this network. I mean, is it reliable? I mean, is the power that it's providing, is it is it, what's the availability? Well, how many disruptions, power losses do we have, per year? How many minutes per year are we out of power? And again, kind of a similar type of graph where we're looking at duration of interruptions as a function of population density. And of course, you can see some spread here, but mostly we're talking about relatively very, very small numbers. So overall, the system has reached a very mature, good state. Certain countries faring better than others, certain countries investing a little bit more than others, and so on. But kind of like a general feeling, in the early 2000s is that there is not much that can be done. I mean, we have built this great system. Okay, we are investing, we are upgrading. It's kind of like evolutionary changes, but not much is really happening. But one way to kind of prove that this was in a way the case is this is research funding for EPRI, and you can kind of see a steady, a pretty steady decline from early 90s to early 2000, and then kind of like plateauing at some level, which in a way is some kind of indication that people got this perception that we have built this phenomenal system, and there is not much that can be done. And you can see also these trends kind of flowing over to academia, where more and more, especially in US, a lot of schools kind of scaled back their power systems majors. They scaled back their power system research programs, and except for few kind of key hubs, there was a significant shrinkage of the investment in the education of future engineers and R&D, as you can see from this graph. But then something really interesting changed. Something really interesting started happening. On one side, we started feeling that there are some environmental changes that we might have caused in the process of populating the planet, and being a little bit careless. And we started kind of being more and more aware that, okay, well, maybe the way we are currently generating electricity and the way we're currently transporting ourselves around is not the best. It's not the best way for our civilization, and that we are starting to induce some serious changes to our climate. And people started looking more and more into renewable energy sources, and kind of, okay, well, what can be done? At the same time, we had like major kind of like technological development, both in wind turbines and also silicon solar cells. The cost went down, the technologies advanced, and several of these trends kind of converged. So if we are looking at the map, here to the left of wind resources in the US, kind of like where the majority is, so we kind of have this big concentration in the kind of the middle of the states. And also, if you are looking at the solar installation, you have kind of significant concentration in the south and the southwest of the US, but other parts are also actually not that bad, especially compared to some other European countries. So interestingly enough, we started to look more and more as like, okay, well, can we tap into this renewable and distributed energy resource, and can we integrate this with the existing grid? I mean, what does need to happen for us to be able to really tap into this resource, and really be able to, for example, in the wind case, okay, can we generate this electricity in the middle of America and get it to highly populated areas on the east and west coast? Can this network do that? Can we also, use solar as kind of like even more distributed and generate locally and consume it also more locally? And what can happen? And this kind of started inducing this new process, which kind of converged to people start saying like, okay, well, there are these three critical vectors, critical trends that are driving this transformation of our grid. On one hand, because of the climate change, we are really pushing towards decarbonization. On the other hand, we are starting to look and think and rethink how can we do more decentralized generation, but how can we also do more decentralized control? And kind of like an underlying trend, not just in the energy and power sector, is really digital technologies and digitalization. So the convergence of these three trends in the past, I would say past 10 years and going forward, have really, created an opportunity for perfect storm. One other critical building block in this process is really power electronics, and power electronics has started to play a key role because most of these distributed energy resources, and not just distributed energy resources, are being connected to the grid via power electronics converters. And we can think of this as, power electronics converter is actually a digital controller for power. So what's happening now, in a way, if we are looking at this kind of sketch to the right, from this kind of highly centralized generation where we had these like massive power plants and then transmission lines connecting to our distribution systems, we are starting to see more and more distributed energy resources popping up all over the network, on the distribution grid, on the residential, and basically everywhere. Most of these devices are connected to the grid via power converters. Most of these power converters now have the ability to communicate. So they, digital communication becomes kind of like a big opportunity, I would say, for us to take advantage of these power converters, which provide many other possibilities to control and stabilize the grid in ways that we have not been able to do before. And the other opportunity is that now, with a lot of distributed energy resources locally on the distribution network, we might be able to actually operate the grid and take advantage of being able to disconnect portions of the grid, operate them independently in the islanded mode, or in case of a big storm or any other kind of major natural disruption, we might be able to recover part of the network and not necessarily rely just on these big, highly centralized remote power generators, but help each other, help each other out with local generation. So we really see in this process power electronics converters that are really kind of key building blocks. So we have smart converters, smart FACTS devices, controlling them in certain fashion, start building microgrids, distributed energy storage, not just battery energy storage, but different kinds of storage, combined with this new opportunity to do more clever digital control, and not only on the local level, but also on the area level, the microgrid level, the area level, and kind of like layer this control is really something that in the next 10 or 15 years will provide a lot of opportunities to create value for everybody that is participating on the grid. And that really gives rise to to this concept is that, you know, we're not just consumers anymore. If we're paying for electricity, we are slowly being turned into prosumers, and we are both producers and consumers. We want to participate on the grid. We want to have more opportunities, and we are trying to make this a more collaborative place and more cooperative place where, you know, people can invent different business models, people can invent different technologies, and unexpected things can happen, not constrained by just this rigid structure that has been, you know, kind of postulated and built, you know, 150 years ago. One of the big challenges in this process, of course, is complexity. Yeah? And this is what everybody's freaking out. Okay, well, you know, before I knew what I was doing. It was, you know, it was pretty simple. It was pretty, you know, it was pretty straightforward. And, you know, we were showing this. Okay, well, you know, we had these big generating units. They were fully under control. We have, like, you know, 5 or 10 or 15 or 20 major synchronous generators. We have very, very controlled channels how we communicate, you know, between them. We have a central controller that is, you know, controlling the frequency offsets and so on. And then basically the distribution network is just considered as load. Whenever something goes terribly wrong, we just unclutch, you know, the loads. We just disconnect them, and we kind of knew how to do this really well. But now what's happening is that the roles are kind of reversed. Distribution network is really starting to take the role of the, you know, both generator and distributor. Instead of having 10, 15, 20 major synchronous generators, you're having tens of thousands and hundreds of thousands and millions of, you know, solar inverters and local battery storage, residential battery storage units, and wind turbines. And now you're also starting to see cars with, you know, currently mostly being kind of unidirectional loads, but also with possibility to become kind of bidirectional, where it's not like just you know, grid to vehicle, but it's also vehicle to grid interaction and power flow. And this complexity now starts to become really scary. And yes, it's an opportunity, but it's also scary. One of the key components, if you think about this, is actually control software and firmware that is really controlling power converters at the low level. When I say low level, meaning on the converter level. And this is something that starts to define the behavior of the grids. Unlike in these, like, older school synchronous generators, every synchronous generator is different. We are starting to see that, you know, inverter behavior again is like firmware / software defined, and that's interesting. It's an opportunity, but it's also potentially dangerous. Yeah? Now all of these converters starts to be networked. So they start talking to each other, and they start talking to higher level controllers. People start worrying, like, okay, oh my God, you know, these are cybersecurity issues. What happens if, and so on. But at the same time, there is this huge opportunity that we are getting these smart devices that can reconfigure themselves, that can disconnect from part of the grid, that can locally control frequency if needed, that can locally control voltage, that can provide some other ancillary services to the grid. And kind of like sorting through this kind of like big, I guess, a big network of opportunities and challenges is a big deal. But one of the one of the kind of emerging complexities on this grid is what I was mentioning, is really software firmware. And my question is, you know, how complex is an inverter controller? How do I put this into perspective? How many lines of code does that inverter have? I mean, is it a lot? Is this not a lot? And there is this interesting website which basically ranks and compares these different devices and looks at, you know, basically complexity of their embedded code compared to by measuring number of lines of code. And so you can kind of see here, there's also, it's a really nice website, and I can share the link with you guys. It's kind of like interesting. Today's PV inverter, you know, give or take, it's on the order of 200,000 lines of code. So if you look at here, 100,000 lines of code, 200,000 lines of code, you know, we are talking about, like, let's say space shuttle. The last space shuttle had, you know, 400,000 lines of embedded code. So that's kind of the, you know, the order of magnitude. Yeah? On the other hand, this is kind of on the lower end of complexity. Yeah? On the higher end of complexity, car software is really something which, you know, has become incredibly complex. It has about 100 million lines of code. Yeah? And there is this whole range kind of like in between, you know, from from few 100,000 to 200 million. And, you know, we are saying like, okay, well, you know, our inverter today is here. It's not like really complex, but the part that we are missing here is, yes, maybe this converter today is 200,000 and tomorrow will be 300,000 and 400,000 and finally gets the size of the code of space shuttle, you know, 40 years ago. But the complexity is that this controller is not by itself anymore. It's communicating with its neighbor. It's communicating with its neighbors. It's communicating with higher level controller. It's communicating with protection. It's interacting with protection. And this is also a similar concept with the car software. Car software became complex because there is network of 20, 30, 40, 50 engine control units that are all networked together on a CAN bus. So here, now we are seeing how this complexity quickly explodes, because locally on the distribution grid, okay, we start having a battery storage inverter that is connected with like local solar inverters. Maybe it's also talking to, you know, local smart loads. It's talking upstream to a distribution network. It's talking upstream with the distribution substation, maybe, you know, like a DMS system. And then, you know, now this becomes a system of systems, and this interaction can give rise to unexpected behavior and then kind of emergent behaviors. And that's that complexity that, you know, we have to think about, provide the tools to be able to design, test, validate, and promote these technologies. Yeah? On top of this, you know, our D3 grid, which is being decentralized, decarbonized, and digitalized, is also meeting or starting to interface with e-mobility. So our transportation platforms are starting to get electrified, and most notably here, it's electric vehicle. And this electric vehicle now starts to become all of a sudden part of this network, starts to participate, and it's not just a dumb load or dumb consumer. It can actually be a smart or smarter. It can interact with and provides a lot of interesting opportunities for kind of changing the way things are being done. And we see this electrification, not just or e-mobility shift, not just in personal transportation. We see that in marine. We are seeing ships being electrified, trains as well, more and more. We're also seeing more and more efforts to put more storage and local generation, fuel cell type of generators for trains, platforms, and so on. So this is really this interesting opportunity, and I like to say, you know, thank God that, you know, this is happening now, because as an electrical engineer, you know, this is really what we can call living in interesting times. I mean, we are really blessed to live in interesting times, because grid is changing in so many ways, and the way we produce, distribute, and generate electricity and energy more global is completely changing. Now, of course, the challenge is that, you know, all these different players are actually interacting on this utility grid on different timescales, ranging basically on the order of 10 orders of magnitude. So if we are looking at these digital power processors, inverters, they are, inverters are switching. We have PWM on the order of a microsecond, and we have different interactions on the level of control, current control loops. We have also interaction between inverter-based DERs, faults, protection and protection coordination. Then kind of like slower timescales, frequency voltage regulation. Then we're starting to have renewable resources, which are injecting this intermittency, load leveling, and so on. So it's really a problem that needs to be addressed at all these different timescales. And that's the exciting part. And one of the systems that I mentioned earlier, which we call microgrids, is really the perfect sandbox to play with these different concepts, understand, and advance the technologies. But then in that next level, this microgrid can become kind of like a building block, this cell, this new cell, this independent cell that can take care of its own needs, but can also interact and become a building block for this more distributed grid. So it's kind of like interesting. A lot of people talk about microgrids. We see a lot of companies, bigger companies, smaller companies playing in this area, and there is this kind of general perception that building microgrids, as I like to think of them as cyber physical systems, is really something of a Lego block type of exercise. What does that mean? Like, okay, well, it's relatively simple. You buy these DERs, you put them together, and you get like this nice house, and everything is working right out of the box. But what we have seen in reality is that it really looks more like this. It's really infinitely complex because of interoperability issues, because of all kinds of different problems and issues that it's just a big big problem in the big mess. And even smaller microgrid projects become quite of a big challenge for people that make them, because it's just the infrastructure is not there and the tools are not there, and so on. So a few years ago, what we did is we actually were invited by MIT Lincoln Lab. This is a big research lab that is operated by MIT, and they said, like, okay, well, can we design a quote unquote competition where we will bring these different microgrid controller manufacturers, and we will ask them, okay, how about you connect this microgrid controller to a test bed? And in order to test and validate, you could not really build a microgrid all the way, but they use hardware in the loop real-time simulation to build this test bed, which I like to call a microgrid flight simulator, and try out to see how quickly they can actually deploy these microgrids. And we had all the big major manufacturers, and turned out this exercise proved to be extremely difficult. One of the big first problems in that is that all these different microgrid controllers were not easily, it was not easy to connect them with these different DERs. They were not speaking the same language. So that was the first problem. You bring your microgrid controller, it's fantastic, but you have your genset, you have your battery storage inverter, they don't talk the same language. So just getting them to talk the same language was a big project. And we learned the hard way that standardizing communications and then being able to have a kind of like a standard communication language or languages is kind of like a first step towards improving these processes. Then different DERs behave differently, models are missing, tools for simulating were not on par, and we realized why every microgrid, kind of the hard way, why every microgrid was, such a big project and so expensive to say. And we see that, even to this day, this is really still the problem. And the test model that was used was called Banshee microgrid, and so we built this digital twin, and all the microgrid controllers were actually classical old school central microgrid control, centralized. So I here have an image where we were playing in one of these exercises, working with Eaton and deploying their microgrid controller that was directly communicating with all the relays, all the DERs and everything, and in a centralized fashion. And we, in the process, so we built these complex models, high fidelity, developed tests to testing and validating, and we really were able to push this infrastructure to the next level. And when I say infrastructure, I mean infrastructure for being able to have your sandbox for designing sandboxes, and that sandbox being your hardware in the loop simulation, with real-time hardware in the loop simulation with all good models and everything, to kind of be able to explore a lot of these problems and push the technology forward towards kind of being more mature and easily deployable. But still, one of the problems was that most of these microgrid controllers, they're all central. They were all centralized. Yeah? So you have point-to-point link to every single DER. You have a problem. What's going to happen? If you lose that link, what's the what's the reliability? And some time ago, we actually started thinking and collaborating with a group at University of Illinois Urbana-Champaign with Professor Alejandro Dominguez to really help him or support his research in building distributed control for microgrids. So what you were kind of seeing there is this state-of-the-art approach where you have this is kind of like a one line here. You have this centralized, I call this like a cyber layer, yeah, centralized controller which needs to talk to all key DERs and smart loads and do it that way. His group at UIUC developed this really interesting distributed algorithm where now all of a sudden you're not controlling DERs in a centralized fashion, but they are actually communicating with their neighbors, and they're trying to reach a consensus about how to control, for example, how to set the reference power point, active power, reactive power, how to control the frequency, and so on. So this is really still an ongoing project, really an interesting project where it was developed. They have developed an architecture for distributed control and coordination of DERs for provision of frequency regulation. So this is one of the services that microgrid can provide. And what's really nice is that DER decision making relies on algorithms that are executed over distributed computing platform, which is now a significant departure from commercially available solutions. So imagine, going from this highly centralized, where you're talking to all the DERs and talking to all the DERs and talking to all the layers, all of a sudden, you're going to this architecture where neighbors are talking to neighbors. If the node drops out, that's not a problem. Graph is still connected, communication still works. Decision making is more decentralized. You can also not just do control, but you can also do optimization in the same fashion. And now this is opening all these doors for more decentralized control, which we don't have to explain what the benefits of this is, and how this, for example, how this would look like on a specific example of the microgrid is that you still have local controllers next to big DERs, but now the main difference is that they are connected to their neighbors. And how neighbors are defined, we don't have to go into these details, but as for example, if you remove one of these nodes out of the network, and if there is still other path, the network works and the control is still achieved, and you are starting to build that infrastructure where it's more decentralized and it's more resilient and more robust. Now, the question here is again, well, these are disparate DERs made by different OEMs. Can they talk to each other? How are they going to talk to each other? And this is another interesting project which I just briefly want to bring up. We're working and collaborating with Duke Energy, and they are developing this open standard for communicating between DERs called OpenFMB. And this is exactly the kind of communication network, communication protocol that was missing and still is missing, that basically allows one to kind of transition from this old school central system point to point where, at the microgrid controller level or the substation level, you are talking directly to every single DER, towards more peer-to-peer communications enabled by OpenFMB standards. So think about this. If you combine distributed control approach with this OpenFMB, which allows peer-to-peer communication, now all of a sudden you're shifting your intelligence from the centralized controller system. You're shifting it on the layer of DERs. Every DER has its own computational capability, and you can run your algorithms here in a more distributed fashion. Still, a lot of systems, legacy systems, and so on will require to be able to pull directly data from certain nodes. That's perfectly fine. But this layered architecture kind of like flattens all the DERs, especially let's say on the distribution level, on the level of the substation, and allows you to communicate and exchange that information. So if you combine this distributed control, which is now not happening, just at one controller, but it's distributed among different nodes, and if you empower these nodes now to communicate, now you're already talking about like a little bit more significant shift towards more decentralized decision making, decentralized control, and most importantly, the ability to scale. Yeah? So the way we have been working with our partners is building these test beds, these digital twins, that now enable them to actually test out this new communication protocol that they're developing, and de-risking, testing, validating before they actually go to an actual site. And this is an actual Mount Holly site that is like modeled here with the digital twin, and then there is here an actual site with actual DERs and actual energy storage, inverters, protection, and basically the whole thing. And now that enables them to kind of quickly transition the technology and accelerate this shift, this move from all the way to deployment, to actual deployment. No? Okay, another piece here that that we are just kind of quickly that I wanted to highlight is that now that we are talking about more and more microgrids, and we really want also to be able to that we also want to be able to maybe operate independently, maybe do a black start, maybe be able to recover our part of the network decoupled from the main part of the network. A lot of researchers and developers are looking into how do you control how do you control your inverters in what is called the grid forming mode. And this is an important the important area which actually Professor Umberto and his team have been developing. They also developed a very nice teaching course, teaching module, explaining and kind of setting up the framework how to think about these different grid forming technologies in light of this kind of shift, in light of the shift and movement towards more distributed and distributed controls. And it's kind of like interesting to look in 1904 in one of these meetings. This is basically before there was IEEE, it was Institution of Electrical Engineers and the American Institute of Electrical Engineers. They were looking at kind of like what's happening when you start paralleling in synchronous generators. That was the problem at the time. Are there going to be like some stability issues? How do you control that? How do they control the frequency, and so on? And now, some 100 years later, we are looking at how do we improve the control of our inverters to move more towards grid forming control, which will bring a lot of benefits, and how do we standardize this as well. Now, the good part here is that this starts to become kind of the control issue. How do you control your inverters, and how do you basically develop the software and firmware? And then here it was more of a kind of like, okay, what do you do with synchronous generators? But nevertheless, very, very simple. I mean, very similar kind of thinking. Before it was done with synchronous generators. Now it's done with digital power processors called power converters. So this is another big kind of important piece of the puzzle towards getting to more resilient, more robust, and more decentralized decentralized grid. We talked about e-mobility. I'll just briefly mention that we are seeing this huge shift also in terms of shipboard power systems. They're being more and more electrified, and this is very, very exciting times. We also like to see microgrid. Ship as a microgrid, and we've been involved with multiple vendors here. This is a very nice, unique project where we worked with ABB in helping them build a flight simulator for shipboard power system that can simulate both AC and DC distribution system. And it's kind of another big shift towards electrifying the shipboard power system, and also providing the manufacturers tools that they can accelerate this transition. So with this, I would like to kind of bring it home, conclude slowly. In the last 150 years, we have seen this tremendous progress from basically starting from DC generators and DC distribution grid to largest to our civilization building the largest man-made network, electrical network on the planet. And now we are seeing a significant shift in kind of evolving this complex network, in making it more decentralized, making it more robust, digitalizing, and of course driving the whole decarbonization and supporting the transition to electrified mobility. So with this, I would like to conclude and hand it back over to you, Fernando.
Oh, thank you very much, Dr. Ivan, for this really amazing presentation. It's really interesting to see this paradigm shift that has been going on from the early beginnings of the grid systems, and now we see more and more new tools like optimization and artificial intelligence and all these new software-driven technologies that are helping and bringing challenges for the power electronics and microgrid industries. And at the same time, that's really challenging. It's really great for us because we now have many, new opportunities to work on. So I hope that the students that are watching this presentation can become inspired, to develop new strategies and new technologies to work on this field. So thank you very much for this amazing presentation. And now we have some time for question and answers, and we have some questions here. Let me see if we have some questions. We have a question here on the Zoom chat. I'm going to read the question, and then we can proceed to the answers. I can see the name of the person who asked the question. I can see the name, but I'll read the question. Dr. Ivan Celanovic, congratulations for your very nice speech. Our digital simulators, emulators, view systems are model-based systems. How to meet the best and adequate model, good accuracy and fidelity for our studies, analysis and design before performed experimental validation or to know these realities. When there are different subsystems, scenarios, power, and scales, with high degree of complexity, including different scales, huge challenges, just with confidence, validated digital platforms, can we use for our designs? Are there other ways to do this? Thank you, and Typhoon, for your support on our events and research and developments.
Yeah, thank you, Fernanda, and thanks. This is a great question. I agree 100% with it's a question, but it's also a statement. In a way, system is extremely complex. We are not just scaling, 10 or 14 orders of magnitude in terms of time scales, but we are also scaling temporal scales and technology scales. So it's like super complex. What we have learned in this process is that, brute force does not work. So although, we take a lot of pride in building ultra high fidelity systems and really, being able to build high fidelity inverter models and then take it from there. But you really, one really needs to be pragmatic and use the right tools for the right problem. And what that means is that it's really important to understand what the problem is. And when you are designing certain level of control, it's really important to understand, what are the time constants of interest? What are the dynamics? What is the dynamics that is of interest? And then choose the modeling complexity and fidelity based on that, so that you can actually get the job done in finite time with finite resources. So I believe that as technology is evolving, it's becoming easier and easier to use higher fidelity models for more complex things, but it just takes time. So I think what is really important is to use the right complexity of the models and to be able to actually validate the models, because every model is an approximation. So there is no perfect model. Perfect is only, nature, physics is perfect. Huh? As soon as we are modeling it, we are approximating it. So I would say it's really important. This model validation is saying like, okay, well, this is the problem that I'm solving. This is the dynamics that I care about. And then can I validate that my model within this space that is important for me for this problem, I'm getting good fidelity and I can trust my model. And this is something that, we do a lot, but it's not kind of completely common practice, is to really do model validation and really understand what's the domain of application, because, every model is good and every model is bad. It's bad if you use it outside of its validity range, and it's good if you use it inside the validity range. So in order to be able to trust the model, you have to have this process of validating it against data set, against measurement results, and so on.
Okay, that's really interesting. We have another question here from John Lenz. He says, hello, Ivan. Thank you for a great presentation. Do you think blockchain technology could be one of the future roads to be taken to achieve this decentralized consensus-based grid control? Or could we take anything from blockchain into our control strategies and methods?
Yeah, this is a good question. I believe that blockchain could provide part of the answer. One thing that is always missing in this discussion of application of blockchain to power system control is physics. Yeah. So, and what do I mean by this is that there is a network and there are physical constraints. What can happen within this network? So yes, theoretically, I would like to trade with everybody, every player on the network, but can I interact with this guy through my physical network? And then also, can we trade, quote, can I buy electricity from that player or vice versa with the given constraints of the network? For example, maybe we are all connected to the same network. So theoretically, he can sell electricity to it and I can buy from him. But then there is this physical constraint that at this operating point, I will not be able to push power through, I don't know, certain tie line to get it to me, and then the system will become unstable. So I think that's the piece of the puzzle in my mind that is missing, is that yes, blockchain is an interesting solution to kind of keep tabs of who is selling and who is buying from whom, but we have to figure out how do we basically clear and allow these transactions to happen based on physics. And physics means that we have to have a good network model, and somebody needs to exercise that model and say like, yes, this transaction is allowed. So because it's slightly different than just kind of typical application space for blockchains where there are no physical constraints. We operate in a physical constrained world. But very, very nice question. I think there is some interesting work in this area, and I think we're going to see more and more.
Okay, thank you, Dr. Ivan, for answering this question. We have another question in the chat from Professor Lucas Belinazzo. He says, Dr. Ivan, thank you for your great speech. Which topics do you advise undergraduate and graduate students to study in order to understand the problems related to DERs and microgrids?
Yeah, thanks, Lucas. Yeah, really good question. I think it's on all the levels. So I mentioned that it's really an interesting big push going on now to figure out how to really deploy. When I say deploy, I mean really industrialize and deploy into products grid forming features. How to enable inverters to operate in the grid forming mode, and that's one level. Then that next level is kind of, in my mind, control of microgrids, distributed, kind of more distributed control of microgrids. Then how do we control ensembles of microgrids, because that's or you can call it how do I sectionalize distribution networks and then control parts of it, but then coordinate among them. So that's kind of like the next level of control. And how do I build? Also, the other thing is how do I build maybe new services or new applications? How do I invent some new applications and new services that microgrids can provide to their users? So I would say really on all levels, on the inverter control level, and then the microgrid control level, and then kind of like the next level, coordination and cooperation between microgrids, and then also being creative and saying like, okay, well, what else can we get out of this now that we have this infrastructure?
We have another question now. I can see the name of this Marcelo Vinicius. Marcelo Vinicius da Paula asked the question. Hello, Dr. Ivan. Very nice presentation. Thanks a lot. Do you think this control you commented about, if it's or not possible to inject or extract power to the grid due to stability or other constraints, could be achieved through AI? By the way, do you think state machine control will be taken over by some sort of AI? What are the horizons for these aspects?
Thanks. Yeah, this is very good question. Yeah, I think, well, first let me see. There is more than one question. I really believe that this is the next frontier, and I think the question is spot on. The way I like to think about this, and I actually heard this from Professor Deepak Divan. So he said the way we have built our grid today, and this applies to microgrids, is really very rigid, and the way you can operate it is very constrained. So he actually compares the way we control and operate grid to a case that, let's say, if I were to sit in my car and drive to the airport, that basically instead of sitting in my car and opening the door and then just driving, basically I would have to first look at every single traffic light on the way on my Google map, and then try to calculate and at which speed do I have to go to hit that first traffic light, and then what my trajectory is going to be to the second one. So very constrained, very rigid, and as opposed to that, I think we really have to think how we build in these mechanisms for more autonomous way of thinking and more autonomous way of controlling our microgrids and grids to that matter as well. And I think this is the area where where we will see huge changes in the future, where basically instead of just kind of doing it in a very rigid way, we try to build some structure to it where it can be more flexible, more autonomous. People can connect and disconnect from the grid without having to ask for permission, or we'll be able to cooperate on the grid. We'll be able to build some additional services, and for that, I think we need a completely different paradigm for control and communication. So I believe that AI will play a significant role there, and I think that problem is probably much better than the autonomous driving. I think autonomous driving is way more complicated, way more complex, and I think AI applied to more autonomous control of power networks is better and more well-defined problem.
Thank you very much for your answer, Dr. Ivan. We have a comment from Ricardo Bortolini. He says, "Hello, Dr. Ivan. Thanks for your speech." We also have more questions coming, and we have some time. So,
well, that's great. I thought that I put everybody to sleep, so that means that I guess it wasn't that terrible. So I thank you guys. Thanks for the good question. Yeah, please go ahead, Fernando.
So we have another question from Professor Lucas. He says, "Here in Brazil, there is no regulation I know about microgrids. Therefore, it would be not allowed for energy distribution companies." Let me read this again. "Therefore, it would be not allowed by energy distribution companies. Do you know how microgrids with multiple prosumers and possibility of islanding being regulated and allowed in other countries?"
Yeah, this is a good question. I mean, it's also pretty complicated in the US, but we are actually seeing changes now, and we are seeing we are very close to basically getting the approval for distribution level microgrids, basically owned by distribution operators. So I think it's still pretty tough and kind of constrained, but things are changing, and I think in a relatively short period of time, it will be more and more liberalized. Let me put it that way.
Thanks, Zoran, for your answer. And we have one more question from. It's difficult to see the names here in this chat. There, so no. from Ricardo. He's asking, do you think that cybersecurity could be a real threat to power systems, considering all this integration and distributed control scenario, and how we could deal with it?
Yeah, I mean, absolutely. It's a threat, and it's a big threat. So it's kind of it's a general. I would say it's a general notion. Closed system versus open system. Yeah, if you have a closed system and enclosed, meaning architecture is closed, but also communication access and so on. If you have a closed system, you have more control over it, and more likely you can control the threats and the all the other issues. But the problem is that you're missing out on the functionality, on the opportunities, on the return on investment, on the new services, and who knows what. And then kind of, I guess, just notionally, open system is something which is more flexible. It interacts with the environment, and that, of course, opens the doors, makes it more vulnerable. So absolutely, it's a concern. But I think in the past, at least, we have and a lot of precedents where open networks in basically many ways managed to evolve and develop in such a way that basically they are much better off than the closed networks, and the threat and the basically downside is much more reduced. So I'm proponent of open networks, and in this case also open control and communication networks, more open. But a lot of work needs to be done so that in the end, you don't end up with much less reliable and much less capable system because of all these other threats. So I think eventually they can win, and they will win. It just needs a lot more work.
Thanks for your answers. Okay, we have more questions coming on. So people really got inspired by your presentation. We have another question from Professor Lucas. He's asking, where are microgrids being built today? More to single prosumer like the university or a farm, or which applications they are being applied to?
Yeah, so it's kind of interesting. Typical it would be highly mission critical loads, and you can see this in US, for example, that being hospitals, military bases, airports. This is kind of first order, because you have mission critical loads, and you have to support them, and that's kind of the natural choice. What I'm seeing now, big shift with accessibility to battery storage, inverter-based large-scale battery storage, is that I see basically more and more industrial customers basically choosing to actually add battery storage, large-scale battery storage to their industrial plants. And by doing that, they're technically converting their site into microgrid. Yes, most of the time these microgrids would operate in grid-tied mode, but there are certain events where they might lose power, low voltage right-through events and so on, where because they are industrial loads, they would benefit from this battery storage moving quickly and enabling the grid, the islanded mode. And the way commercially this is starting to be a reality is that this battery storage, once you install it on your site, is providing value, generating revenue for you in more than one way. So if it's just, okay, I put this battery storage, it will save me like 5 minutes or 10 minutes or 15 minutes during 1 year. Commercially, maybe it's not still making sense, but now I can also enlist that battery storage to participate in the frequency regulation on the wholesale market. Okay, well, I start making money by my battery charging and discharging and participating in frequency regulation. Then potentially I could also be doing some, not potentially, but I could be doing some peak shaving of my load and reducing cost of my electricity bill by doing that. You can also shift some power consumption. Maybe I have some renewables. So I'm seeing microgrids becoming more commercially available because financially it's starting to make sense when you can do what my colleagues from Hitachi ABB, they call it value stacking. Yeah? So if you just put your battery storage to have this microgrid in the islanded mode for a short period of time, it doesn't make sense. But if you can make money with like additional ancillary services and additional things, then all of a sudden it starts making sense. So it's a good investment strategy. When it's a good investment strategy, people find out a way how to push government and enable it, and kind of open it up. So I see this slight shift happening where commercially it's starting to make sense because it's commercially now of course not everywhere, but there are certain feeders, there are certain parts of the network where weak grid, unreliable, important load, or mission critical load, or industrial or commercial site, and then this is catalyzing the change. So I see that as a driver.
How is the market for these ancillary services in the US and in Europe now? Is it evolving fast, or is it still moving slow in this direction?
In US, it's actually pretty good. I mean, I don't know for all the utilities and all the states, but a lot of them you can actually enroll. Let's say you buy your battery storage, you can enroll it in frequency regulation, this AGC. So you basically get this AGC, signal automatic generator control. We were talking about synchronous generators. That's what they developed to control the frequency on the distributed generators. You get that signal, you follow that signal, and you're getting paid. So it's already a reality. It's just that you have to stack few more value streams to really make it commercially viable. And I think then it will scale more, because then then it's not subsidized, then it's making money on its own.
Yes, that's quite interesting. I also have another question. When you were talking about standardization and then open networks and open controllers, so how is this going in industry right now? Is there discussions and works already going on in order to provide some sort of standardization for microgrid controllers and these management systems?
Yeah, that's interesting. I mean, for example, Duke Energy, they're big proponents of this open FMB, and I think it's a very, very nice solution. So open FMB is completely open standard, so they're not developing that for themselves. They're developing because they notice there is a huge need, but they're developing it in such a way that it's open, open standards to anybody. I mean, that's the reason how you can. That's the only way how you can win and become a standard if it's open. And but I still see that most manufacturers are doing their own thing, because it's human nature. You think, okay, well, I will be the one who will persevere, and everybody will use my approach. So I see still a lot of fragmentation, and everybody doing their own thing, and because of that, and because of not significant enough pool, it's still everybody doing things for themselves. So a lot of room for improvement. But I think as some of this as the commercial environment is changing, I think mentality will also change, and things will change too.
Thank you very much for your answers, Dr. Ivan. And we don't have more questions here on the chat, and also we don't have more questions on the YouTube chat. Just let me check again. Okay, we have another question. I think this is the last one before we finish this first presentation. So Professor Lucas also sent another question. He's saying, being a single prosumer, single owner in a big microgrid, does it make sense to have multiple microgrid optimizers to reduce energy costs or maximize profits?
I think so. I think it makes perfect sense. Yeah, absolutely. Absolutely.
Okay, so we don't have more questions. That was our last one. So I thank everybody again for attending this first presentation of our CEPOC 2021. And we would like to thank Dr. Ivan again for sharing some of his time and some of his experience with us. And I would like to encourage everyone to attend our panel discussion that will begin in half an hour, more or less. It's 3:30 p.m. So in this panel discussion, we will have again Dr. Ivan Celanovic. We will also have other guests, Zoran Miletic from the Austrian Institute of Technology, Leandro Della Flora from Danfoss Drives, and also Professor Humberto Pinheiro from UFSM. So you will have the opportunity to ask more questions, and we can make some interesting discussions later on. So with this, I finished this first plenary session. And thank you everybody for attending, and I hope to see you all again in a few minutes.
Thank you so much.